Come back, and yes, now as I have told, I have found that little typo error which we have made. It was, I didn't notice that the transpose was already performed here in this command, which I copied. I copied it here, right? And that transpose is already performed. And basically what I did is I reversed that transpose with this line. So the idea is, for example, with the same example which was shown to you before, if we convert that into the column and in the row, like this, the order is incorrect, right? So we need to actually first transpose it and then convert into the column and then into the row, like this. So that's the basic procedure, right? However, this matrix R during its definition time has already been transposed like this, right? So if I did transpose again, I get this matrix, and after converting into the column and row, I would get incorrect numbers like this. And naturally, the symbols received and transmitted didn't match in that case because the order of them was incorrect. So we can correct that error by simply removing this line, as it's been shown in the practical exercise guidelines like this. There was no such line at all in these guidelines, as you can see, and that fixes the problem. So we run the program. We have 0 errors and 0 error probability for signal to noise ratio of 100. For signal to noise ratio of 10, there will be some errors, 2 errors from million, right? In this iteration, if we run multiple times, however, this number might change, but well, yes. So for example, now it's 3 errors, but not by large margin, right? If we have, for example, 5 signal to noise ratio, then we will have much more errors, right? So your task is to go through those signal to noise ratio values, fixing the error probability and number of errors, and this picture. You need to put them into your report, and that will be the report for the task number 6. So yes, that does it. Yes. So basically we have finished the last practical exercise which affects your grading. So when you send me them, you will get your points for your grade, and at the end of the semester, which is 27, I think January was for you, or 28, something like that, right? So at any rate, I will update that information at the information of the course here, right, at the very beginning, about exam, about when exam tasks will be ready for you and when you need to send all your works, right? So as we have discussed. But now let us return to our course project, and I have uploaded additionally 2 templates for encoding and decoding functions. Well, again, they are in reverse order. Let us change them in places. So first is encoding function for Hamming codes, and the second is decoding function for Hamming codes. You need to download them and put them into the same folder where we have our BER simulation program, SimBER, which we worked on last week, right? So let me first remind you how it works, and here is, let us keep it not much value because we will make a lot of additions to program and we'll need to run it multiple times. Now it's set to work with amplitude shift keying for me, right? So let's see how it worked. So it performed simulation with different signal to noise ratio and counted the number of errors during the transmission, right? Afterwards, with a red cross, it marked theoretical value for the specified for you in your course project parameters signal to noise ratio. Again, let me remind you, it is specified here. For me, it was 12.0 decibels. right? So that's where we stopped. Now our plan is to add another line to this plot, which would be for coding. It would look somehow like this. Of course, it's expected that the error probability will be lower after we use the code designed to correct errors. That is the whole idea. The only question is what kind of improvement can we hope for your specified code and modulation type. That answer will be different for each of you, but overall, naturally, there will be a gain in coding. Right? So you will have some gain. So if you previously, for example, had error probability 10 at the degree of -4 at, let's say, 14 decibel, now you will have at 11 decibel, which is better, right? Because 3 decibel is actually, let us calculate it, 10 at the degree of 3 divided by 10 is almost 2 times better, almost 2 times, right? So 3 decibel almost means that you can have twice as weak signal if you use coding and still have the same error probability as before, which is a lot, right? So basically, we are going to test this thing out. So for that, we need to work with this program, BER, and additionally with these two files you have downloaded. So I have multiple versions of these files I was preparing, but we will work with encoding Hamming file and decoding Hamming file. They are organized as functions, meaning that you can call them in your code like rand-n, like reshape. In the similar way, we will call our function called encoding, for example, and specify parameters such as data to be encoded and code parameters m and k. Right? So let us start by actually adding some data to this code what we already performed. So first thing we need to specify are coding parameters. So in my case, I have code word length m equal to 7, and I need to specify that in my code. So here we have a new section called error code correction code parameters. That would be m equal to 7 and k equal to 4 in my case. So actually, let us calculate r by setting to cell log 2 of m. So that's how we calculate the number of correction symbols given this number. And then k, number of information symbols, is just a difference of the total number of symbols and error correction symbols, right? So this way you can calculate for your parameters. That's first thing we need to change. Next thing is here in our for loop, as you can see, we had the same name k. We don't want to misunderstand this k and this k. So for security, we are going to change this number to some other, for example, L, which we are probably not going to use. Here L, and any occurrence where we use that k, actually that would have been much safer to use find function, not match case. Check no. Here, yes, we need to change that. Here as well. And no, this is okay. That is new parameter we need. That is this function cron. check. Okay, it doesn't find anymore these values k, so we have fixed them all. So that's just a precaution, because, well, if we use k value inside of this loop, it will rather take this k, which is from 1 to m or to length of SNR, right, which is a lot, instead of this k, which was the code parameter. Of course, we could use different name here, but it's common to name code word length with m and information block size with k. So we are going to use that notation too. So now, in fact, we can perform coding. Yes, and we are going to perform coding before modulation. That is according to the schematic of the entire diagram of the entire communication system, which we discussed on our very first lecture, right? If you remember, then the diagram looked somehow like this. We had formatting, then we had source coding, then we had channel coding. This is exactly Hamming coding. Then we had modulation. So we need to perform coding before modulation. Then we send data into the channel. Here we add noise. Then we perform demodulation. And then Hamming decoding. So Hamming coding will be performed before modulation. Hamming decoding must be performed after demodulation in the receiver. Right? So that was the general structure of communication systems. So this means that encoding must be added somewhere here. Right? So Hamming encoding. I'm going to mark somehow this new part of the code so that it's easier to see modifications. And in fact, you know, maybe we should save this as new file. Before we didn't make much difference into it, so just that in case we have a new file. I call it SimBER2. I already had some version of this file, but I'm going to make a new file. So SimBER, which was previously obtained, just in case I still will have, right? So Hamming encoding. For that, we are going to use this function and Hamming, which we still will need to make. And this function first needs to be filled in before we can use it. So basically, we need to specify encoding matrix. I will show you today for each of the codes. So that would be cyclic codes, group systematic, and group non-systematic, right? So let us start with the simplest case, group non-systematic code. And then I will show you how to obtain the rest of the matrices as well. So group non-systematic code. For that, you need equations of your coding device, which we already discussed how to calculate. From these equations, you must write matrix based on C, which are information symbols. So there is no C1 in the first equation, so it's 0. There is a symbol C2, that is 1, C3 as well, and C4. Now, in the second row, there is C1, C3, and C4. And in the third row, there is C1, C2, no C3, and C4. That is how we obtained this matrix of the encoding equations. Yes, it is this matrix. And we are going to use this matrix to create encoding matrix for non-systematic code. For systematic code, you are still going to need the very same matrix, right? However, the columns in this resulting matrix will be organized a little bit differently. So I'm going to actually fill in that matrix into the mat file and thus complete the function of encoding. So here we need to input that matrix. And let's see how it's designed. So first of all, we need to have 4 rows, not columns like here. So we transpose this matrix. After transposing, this matrix will look like 1, 1, 0, 1. No, sorry. Yes. Yes, 1, 1, 0, 1. Next one is 1, 0, 1, 1. And the last one is 0, 1, 1, 1. And then that represents a symbol E1, error control symbol E1, that represents E2, and that represents E3. Right? So we put these columns into respective positions of the non-systematic code word. For non-systematic code word, the error correction symbols were located at the positions of the power of 2. So that's power of 0, 2 power of 1, 2 power of 2, and next one would be after C4, 2 power of 3, 8 position, then 16, and so on. Right? So this first column goes here, second column goes here, and the third column goes into the fourth columns. The remaining part is the identity matrix, right? So here is 1 and res 0, 0, 1, zeros, and so on. So basically, now I need to input that matrix into Octave file. Let me actually somehow reduce this window so that I can see this matrix. Okay, I can see that matrix now, and let us input that matrix. So the first row is 3 ones and 4 zeros. You will have longer matrices, so you need to be careful when you input that matrix not to make mistake. Right? In my case, it's simpler, but the approach is very same. You still need your equations. You generate from equations these 4, 5, how many you have columns, and the rest is filled by a diagonal I matrix. And the last row would be this, right? So we have this function which now performs encoding. Let us test this function in this command window by using some code word. In fact, let us use the very same which was used in an example. Here, for example, here we used the code word 1010. So that was our data. Let us denote it with X 1010. And then we specify it to our encoding matrix like this. Enc Hemming, data to be encoded, the first parameter, and the rest parameters are M and K. For my case, M is 7, K is 4. In fact, we have these values, so yes, we can even specify them like this already. And no, M is unspecified. K, however, I see. Okay, let us copy this line, and then they will be specified. I needed to execute that program at least once in order for them to be specified. So we have obtained this non-systematic code word where we have data block in original way 1010 and the control symbols 101. Let us see if that was calculated correctly. Yes, it is the very same code word. Yes, 1010 and 101. What is the best about this function is that it actually performs the matrix calculation. Let us see how it operates, right? So basically we multiply our code word row of 4 symbols with this matrix and then calculate by modulus 2, right? And that is the encoded code word. So basically this means that I can specify as many code words as I want. So for example, let me replicate this X 4 times. So now I have 4 code words and I can encode them into one go. Sorry, I didn't save that X, right? This. So that is the new X. And alternatively, I have calculated 4 code words in one go, right? In the matrix multiplication way. So what we need to do is to split our data into these code blocks, right? So first of all, that is what we need to do before we can perform coding, because right now our data is just random number generator data of 10,000 bits, which are no way organized. Now we need to split that data into the information blocks with length k and create a matrix of data. So before we can do that, actually, we need to make sure that it is possible to split this number of data into k. So in my case, n is 10,000, right? K is 4. I don't know why it's 3. K is 4. Wait a minute. And R is 4. Okay, sorry. Something is wrong here. I see. Here, we needed to plus 1 make here, right? So K must be 4 and R must be 3. K, R. Okay, that was an error, right? So we need to put plus 1 inside the logarithm brackets, not outside them. Now, if we divide n by k, that is 2,500 blocks, right? Now, however, let us take some other students parameter. Let us say 29, right? M is 29, and see if it is possible to split these 10,000s into blocks in that case. So M is 29. I'm going to output this data, so I remove semicolons. R is 5, K is 24, and if we divide with K, you can see that it is impossible to create the integer number of blocks. So what we need to do is to generate adequate amount of data. That's why we need here, before we generate data, to calculate the correct n value, update that value. So what we are going to do is to calculate this n by rounding down. So in this case, we would have 416 this ratio, or n divided by 4, and multiplying, sorry, not 4, but k, and multiplying with k. So this way, floor n divided by k multiplied by k, instead of 10,000 data, we would generate this much data, which is very close, and this much data can be divided without a remainder with the length of your information block, which is 24 in this case, right? So that will give precisely exact number of blocks. We need this in order to use reshape function. So because otherwise reshape function would say that it's impossible to create such a matrix, and well, we cannot help you. So that's not what we want. Let us write it like update number of bits to be sent, match information block size. Now we generate required amount of data and it can be reshaped. So let us create the matrix of the data as BER matrix. by using reshape function so that each row of data is actually code word, right? So we are going to reshape our vector SB into a matrix with column or the row. So here we have data. We need a row to multiply with this column, right? So we need row, and the number of rows. Wait a minute. Let me check it again. So we have, for example, some vector from 1 to 10. Then we are going to reshape that vector into 2 rows and 5 columns, like this, right? Okay. And sorry, see, there is the same problem. We hope to get this one as the first row and this one as the second row. But we got something different because by default, the first dimension for MATLAB and Octave is column-wise. So we need first to reshape it into otherwise, like this, reshape x5 by 2, and then transpose it like this. The very same problem what was for quadrature amplitude shift cake, and then we will have them in the correct order, right? So we are going to use the same approach. Now we need to reshape into the k columns, which is the length of our code word length, and n divided by k, what's left, that is rows, and then transpose it. This way we generate matrix of code words. Well, it's not yet code word, of information blocks to be coded, right? Then we can use this matrix as input data for our encoding function. So we are going to encode data, encdata, by using enc_Hamming for this matrix and specify m and k. So that is where coding is performed, encode data. We need to encode data only once, because afterwards we are going to modulate it, then we apply different strength of noise, but still to the same data. So encoding is performed just once, and decoding will be needed for each signal to noise ratio. So this will generate a matrix as well, right? So let me show you again that X was this, again X like this, and Hamming generates the matrix, which we need to again stretch into the single column. So we transpose this matrix first, then write everything into a single column, and then transpose that column, right? So this approach will be used multiple times today. So if you are not really certain you understood completely, so it's better for you to take some short matrix like this and experiment a little bit. So you see that that would be Y matrix, for example, and I'm going to transpose that matrix Y in order to get this, right? Then I'm going to write it into a single column, right? And ultimately, I will transpose it once more like this. And then I will have it into a single row where this code word is repeat it multiple times, right? So if you are unsure you understand that completely, I advise you to experiment a little bit, but we are going to use that for our encoded data. Data transposed and data is unwrapped and transposed. So that would be force, or I mean unwrap data into single row. That would be our data to be transmitted. So we need to change this as BER to Encdata. For each modulation type you might have, I have 3, you need only 1. But I'm going to demonstrate you that it works for each of them. Right? So I forced to work on each case. Right? So the modulation process is remaining otherwise intact. Then noise calculation is also the same. And the difference here is that we compare this demodulated data with encoded data because, well, now we have different data. We could, of course, create 2 simulations, and 1 simulation without coding and second with coding, but the nice thing about this approach is that actually after coding this data, you get more data. And in fact, I think we should update this value n to represent this length, because, well, now we will have different length of the signal, and this n, which is here, will be incorrect value right now, and this will lead to incorrect estimation of the error probability and incorrect plot as of such. So we need to actually find the new value of n, which was after you added some correction bits, right? You had information bits, and now this function added correction bits. For each 4 information bits, we added 3 correction bits. So basically that is almost twice as much data now before coding. So we need to take into account that we increased the number of data. We didn't correct any errors yet, so we are going to see what happens if we do nothing about it, right? And then we are going to correct any errors and see how it improves. So that is another update of number of bits. Also, actually, I think we might be needing later the old value of n. So for any case, we are going to back up our old number of bits. Info bits, right? Just information bits without correction symbols. So yes, because after decoding, we will have again only information bits. The control bits will be skipped, and, well, we will need this m in that relation. So this part should work as it worked. Let us see if we made anything worse. No, everything is working just as it was. The only thing is that this curve became a little bit more smooth, basically because, well, our n now is not 10,000, it is 17,500, which is more data, right? Which is basically because of the error correction symbols, which we added during the coding. Now, here, we perform demodulation as before, and then actually, here, we are going to add decoding. Hamming decoding. And again, compare results with original data. So for that purpose, we are going to use accordingly this function, Hamming, dec Hamming. Once again, this function will calculate the matrix multiplication, which can be seen here, code word multiplied by syndrome matrix, modulus 2, and perform error correction. I will explain that as we go. The only thing you need to understand is naturally the coding program is much more complex because you don't only need to find some control symbols or syndrome, you also need to figure out where you need to apply the correction. That is basically why this program is much greater, much harder than this, where you only needed to input this matrix and that was it. Right? Here you will need to do multiple things to account for that. Well, actually, you will only need to comment and uncomment certain lines depending on your code and input syndrome matrix. And that's all you need to do in this. This code has been provided for you because, well, it's actually tricky to make this one on yourself. So, and of course, now we still need a matrix of the code words as input for this code. Yes, so you see matrix with m rows. Each row represents a single code word to be decoded. Right? M columns, not rows, in fact. The row length is m. So m is code word length, k is number of information symbols. We will need that to specify as well. So before we can do that, we need actually to add here syndrome matrix. Syndrome matrix for non-systematic code is very simple and obvious, right? So syndrome matrix is just the numbers from 1 to m in binary form. So here we have 1, 2, 3, 4, 6, 5, 6, 7, right? And we need to input that as a matrix of syndromes in our program, like this. So let me open up that code and let us do that here. So don't remove this to be continued symbol, like, because this way you can start writing in the next line like this, well, which is just more visually and conceptually understandable, right? So I put in all the syndromes of the matrix into this code, just as they are. If you have longer code, you can actually, again, figure out how can you use for non-systematic code. Well, non-systematic and systematic for group code only, right? You can actually figure out how to use Decoding for numbers from 1 to m with r bits equal to 1, like this, right? So it will generate that for you with just this simple line. But you also can anyway input this by your hand, right? Actually, I'm just going to finish it up. And for cyclic codes, you will have to do that anyway by your hand, right? So you will need for cyclic code this list of syndromes. So this is the error decoding matrix which calculates syndromes. Then these syndromes are converted into the number, decimal number, very same way as we did that for count 16 today. And this syndrome value is actually the position of the erroneous bit. Here we have additional check because, well, for example, the very same M29, right? Or, well, better even 21 can happen double error, right? As you know, double error in this case would show, for example, that the error is in the symbol name 28, but you don't have 28 symbol, you only have 21 symbol. So you need to check if the syndrome is actually in range of the actually existing symbols. If it's not, then we will do nothing about it, because otherwise we would introduce a new error, which we don't want to do, right? So here is additional check as an logical operation. So if this check fails, we get 0 and syndrome and index of correction is 0, so we don't correct anything, right? And if it's true, so the multiplier is 1 and it just goes away and we have only syndrome value. And syndrome value is then used as index, right? Index to correct the error here, yes? So we use this index to select error vector, right? So let me show you how this matrix looks like. Rrec. This is actually the matrix of the error vectors, this one, right? Which is diagonal matrix. And the first row is actually the case when we don't have any errors, because we need to work with that too. If we don't have any errors, we don't need to change anything. So here is the line of zeros, and here is the corresponding error vectors. Yes, and the index, this index points out for each code word which error vector we need to take to correct the error. Yes, so for example, if error has happened in the symbol number 5, we would get this syndrome that would be converted into the number 5 and then used as index to select this error vector to apply it to code word, therefore correcting the error in the 5th position, and then we just read data from our well, code words. Yes, I'm now explaining in case well, you actually are interested in the details, right? So after I explain, we will be much faster and briefer. I will show you how to generate other matrices and it will work, right? So that's how this actual error correction is performed. Yes, we add by modulus 2 error vector to incorrectly received code word, or correctly, we don't know that, yes? So error vector can be either all zeros or any of these 7 vectors in my case. So if we don't have any errors, that will add zeros, doesn't change any data, and well, nothing is changed. If there were error, so it will add a corresponding error vector and fix that error for us. Now you need to uncomment correct line depending on your code type. If you have group code, we uncomment this line. Well, basically in this line, we calculate, we select only symbols in non-systematic positions. We only select these symbols because, well, code word includes also error correction bits, which we no longer need. So we need to remove them away from our code word and read accordingly 3rd, 5th, 6th, 7th, 9th, 10th, and so on symbols. And well, these indexes have been calculated for you here. So index A is for error correction symbols, and they are powers of 2. As you can see, if it's actually power of 2, then after division by 1, it should be an integer number. So these symbols are located there. And this is a logical array, right? So, well, actually, let me demonstrate how this works. So, for example, I have M7, and this will produce this logical array. So here we have error correction symbol, here we have error correction symbol, and here. In those positions are error correction symbols. We are interested in reverse of that, inverse of EDX, where are located information symbols. And we use these indexes to read according columns from the matrix, right? That's why we uncommented that line where we used IDXC here, right? Otherwise, for cyclic code, we would use a systematic error, systematic form, right? First case symbols should be read. from the vector, because first is the information part, then is the error correction bits which could be skipped, right? For systematic group code, we are still going to actually use non-systematic detection algorithm because it's much more convenient, but we are going to convert our systematic code word into non-systematic code word with this. You don't need to uncomment this if you have cyclic codes or non-systematic codes. That is only for systematic group code, right? So we have filled in this file and now can perform the decoding. As I have told, first we need to actually create a matrix of the code words. So we are going to actually reuse this and name it somehow different, right? So that would be, let us say, code word cd where the well, maybe mtx, right? We are going to reshape demodulated data. We need to have m rows and divided by m columns and transpose, right? So that is matrix of code words to be decoded. Then we can use our function to decode data, decoded data, dec Hamming, and first argument is going to be this matrix, then m and k, and that's when that old variable k would backfire on us, because here you can see we are actually using k inside this for loop. So if we wouldn't change this for L, we would get errors, right? So this way we made sure that this k was actually this k, not some full temporary variable. So that we did good job. Of course, I knew that from the beginning, but well, I wanted to show you that it's better to plan for that thing. Again, we are going to need to perform these reshaping things, right? So first we are going to transpose, then unwrap into single row. So actually, let me just copy this and change enc to dec. Well, that is needed in order for us to be able to compare data. And now this data is actually this data after sending it into the channel with noise and correcting any errors we were able to correct. So this includes error correction. And let us count the number of errors this way. Yes, so I'm going to copy this and add it here. Num error 1, let us call it differently a little bit, and we compare decoded data with originally generated SB data. Accordingly, that would be BER val 1, or let us say C code, or corrected, better yet like this. And here we need to take into account old number of data which have been actually generated, not including the added by coding, right? So here we added some extra data for error correction, and we need to take into account only actual information symbols, which we have backed in time here. So that is called M. And well, let us see if it actually works. But first, let us add an output here. So that would be uncoded BER. And likewise, we are going to add coded BER. And here we need to output BER val CL. So let's see if it works. Well, it does actually work, and it seems that it works correctly, because as you can see, the error probability, for example here, without coding, is actually higher than with coding. So coding did help in our case, right? Actually here we have 9 in this third position after comma. Here we have in the fourth. That means that we have improved the error probability in 10 times, right? Which is significant amount. Here we don't meet any errors at all. However, for uncoded, there still happen to be some errors, right? So this is considered to be a success. The only thing that is left is to actually plot that line nearby here to show what exactly is the gain. Let us do that. For that, we are going to just add additional line with x-axis SNR and y-axis BER val C. And let us add a legend as well at the end. So that would be legend. First was uncoded. Next is coded. And the last is theory. Right? That red cross on the line. And see how it works. So, as you can see, we have some coding gain, and for our theoretical case, we have a gain which can be evaluated accordingly by subtracting this SNR value from this SNR value, right? So that is the benefit. Let me increase the number of symbols to be transmitted for now by 10 times. I'm not going to put million because that would be a long time, and we still need to check 2 other coding methods. So I will try to keep time, right? So this now works a little longer. Now, if you look carefully, actually, you might find out that in these 2 cases, the coding did worse for us a little bit, because, well, actually, this percentage is a very bad channel, right? Nothing can really help. Well, not let's just say nothing, because as you know, Shannon has proved that you can actually improve this channel. However, it would take a ridiculously inefficient code, but it's still possible, right? So if we zoom this out, you can see that actually for Hamming code, there is, for this low signal to noise ratio, a worsening. However, this is observed very shortly, and for your case, it might be longer, but still what you need to understand is that at any rate, this condition system is just unusable. So it's okay. It's like we will have not 25% of errors, but 26% of errors. This is still nowhere near to 1 per 1 million, which we strive to achieve, right? This is the desired ratio, not 25%. So this is okay. However, if the signal to noise ratio is decent, right, you will have significant gain. And that's the idea. So if we change the modulation type, everything should work. Let me just show you, for example, frequency shift keying. Let me just give this to 5. So now I'm going to use for frequency shift keying, and that would give accordingly almost the same coding gain. So this coding gain you can expect is actually not changing depending on the modulation type. It's completely defined by the code you are using. So different codes will actually produce different coding gains. So that means that this difference between those 2 lines will be different for each of you. Well, not maybe exactly each of you. For example, those who have 31 multiple should have 31, will have same coding gain actually, right? So here we have 31, here we have 31, here we have two people with 27, they would have the equal coding gain, although they have different modulation types, right? Still, the gain from the coding will be the same. And for frequency shift keying, well, it's too less data to be able to accurately tell here, right? But if you increase the number of data, well, that is working. As you can see also in this case, it didn't make worse at the signal to noise ratio 0, but if we go negative signal to noise ratio, meaning that we have stronger noise than signal, that would be the case. Then we would have here. And one more thing, one student correctly said to me in his report that he found it maybe not clear, not obvious, that asymptotically we are approaching to the value representing 0.5, meaning 50% error probability, not 100 probability. So meaning that if we have minus infinity signal to noise ratio, then BER would actually achieve 0.5, not 1%, 100%. Because, well, actually, imagine if you know for 100% sure that all your data is incorrect, so meaning that you receive this data and you know with 100 probability percentage that this data is actually opposite, then nothing is preventing you from inverting the data and receiving it correctly, right? So this means that we could send data at as low signal strength as we'd like. Just knowing this fact, we invert all the data and, well, it's fine. That would be nice if it was so, but unfortunately, actually, the error probability is close to 50%. So it's absolute chaos. Yes. There is no way to find out if there is error in symbol or no. And that is the worst case scenario, which happens to be only if we have a very bad signal, a very weak signal and a very bad channel, right? So that is something to keep in mind, that this error probability will never achieve 100% here. It will always strive to achieve 50%. And that is normal, right? So I will keep this frequency shift keying for now. Now let us see other case of the systematic group coding. How can we make that? So now for those of you who have systematic coding, you need to actually create another encoding matrix. So we need to modify this file accordingly. And in case of systematic coding, first is the I matrix, right? And then is this matrix formed by encoding equations matrix, right? So we have this encoding equation matrix transposed and put in here. So basically, that means that we only need to change this matrix. The other part of this program in any way shouldn't be altered, so all the work you need to do will be in this dec Hamming and enc Hamming to change the coding type. So let us input this matrix for systematic code and see if there will be any difference between systematic and non-systematic coding. Well, a little spoiler, there shouldn't be any difference because these codes must be equally effective, right? So let us find out if this is actually the case. You don't need to do that in your course project. You only need to look at your task, which is given to you. So if you have, for example, group systematic, then you cover only group systematic code, right? You don't need to make cyclic, you don't need to make non-systematic. You only make what is given to you. But of course, I cannot deny you if you are interested in trying. That will be also quite welcome. So you are welcome to try because, well, actually, if you have group code, it's not difficult to create systematic and non-systematic versions, right? So another talk is cyclic code, but currently I'm thinking that most probably in your exam tasks, I will complement these codes. So basically, for example, Leo has group systematic code, meaning that in course project, meaning that in exam, most probably he will have cyclic code, right? So this way you will be able to cover both of the codes. So I want you to know that if you plan on testing other codes as well, you will still have a chance to do that in your exam tasks. So let me finish this matrix. 0, 1, 1, 1, 1. And now this is for encoding. Nothing else needs to be changed because then we multiply our data with this matrix. We calculate modulus 2, and that is our code word. Now we need to change this file as well. Now, there are two ways we can do that. First of all, we can actually change this syndrome matrix as well, and accordingly, we will need to figure out some correction for indexes, similar as it's done for cyclic codes here, and apply that to the and additionally to modify this error vector table so that this is the first row, this is the second, third, fourth, fifth, sixth, and seventh row, right? That is quite a lot of work, and actually it would be quite convoluted and difficult to understand how error correction is performed. So another way is to actually reformat our systematic code into non-systematic, that is performed here, and furthermore use it as it was before for non-systematic code without changing anything here. So that's a good idea, right? And even more so during the drawing of the diagrams. Let me show you here. Cyclic here, right? When we discussed the schematics, we have told that actually systematic and non-systematic codes differ only in one thing, how you line those wires up. So basically here, if you want to receive non-systematic code, you could send first here, second here, third here, fourth here, and then E1 here, E2 here, and E3 here, and that would be non-systematic code. So you just rearrange the symbols, and that's exactly what we are going to do in this program, because it's a simpler way to go. So for that, we are going to use indexes of the error position symbols, right, and information, error control symbols, right, and information symbols, data symbols. So we uncomment this line, 3 lines, I mean, and that's it. The rest should work correctly, right? So what we do here, we save up, backup our code words which have been original, because we will need to access that data. Then in the position of error correction bits, we read accordingly last columns, last error columns, right? So we basically, what we do is basically reformat it. We have, for example, this kind of matrix, right? So we put this as the first column, this as the second column, this as the fourth column, and the rest, accordingly, this would go as the third, this would go as the fifth, this as the sixth, and this as the seventh. So the first line here reformats these 3 columns, right? And the second line reformats accordingly this. So let us see how it's working. I am still going to use frequency shift keying, and for the cyclic codes I'm going to put phase shift keying. So we already see that the error probability is decreasing, and that's a good sign. That means that we don't have made any mistakes. Well, actually in this case we could hardly do. If we input correctly that matrix of encoding equations, then everything is fine. And you can already see that no more errors happen after this signal to noise ratio. So meaning that, well, actually it's equally effective. These warnings are caused by trying to calculate logarithm of this zero, so pay them no mind. It's not something critical. It just complains that it cannot draw some points, right? And as you can see, yes, we still have the gain for using systematic code over non-systematic, and well, basically the picture itself looks quite similar, right? So now let me put on the phase shift keying, BPSK. Again, you only need to do what is asked from you, not really necessarily to try different things, because, well, this program is quite complicated. I quite understand that, but also it's quite, I think, interesting to study how these codes improve results, right? So hopefully you will also find that interesting and worth of that time investment. And well, let's see how it works for phase shift keying. For phase shift keying, that error probability will very fast go to 0, right? Already at the 7 decibels we are at 0, and well, up to 15 decibel there will be no more errors, right? So it's working also correctly. The only thing is that I didn't actually change X accordingly here. Well, might as well correct that mistake now, because theoretical error probability would also change. Right? And I see that old value have remained. So this is the correct value. This one new, right? This one wasn't correct. So that works correctly. Okay, so the last thing remaining are cyclic codes. How do we create a matrix of polynomials of encoding and decoding for cyclic codes? I have promised you to tell about that thing when we talk about this simulation. So also I have found a nice short video better explaining what I'm going to tell you now. So the idea is quite simple. The encoding matrix of the cyclic code is consisting again of two parts, very similar as it was for, well, I have, I think, closed that. Let us open it again. Very similar as it was performed for systematic code, group code, because cyclic codes are also systematic, right? So here we have I matrix, and the rest are something different, right? Let us just say so for now. I will right now explain what exactly is put in there. So this is part I matrix, and this is something different, right? So what exactly is different in this second part of the matrix? That matrix is generated from generator polynomial, which is specified to you as well. So how is it generated? So it will now show you a little bit lower, right? So the first row is actually polynomial of 1, 0, 0, 0, 0, 0, 0 divided by the generator polynomial, like for example 1, 0, 1, 1. The remainder, right? The second line is this polynomial by 1 0 shorter, by 1 power shorter, right? Divided by the very same generated polynomial. And so on until we, well, get to the n minus r, which is, well, m minus r, which is actually k rows, right? So we already calculated those. They are nothing other than syndromes for our error vectors. This is error vector, and the remainder is the syndrome. So that part we should have already covered in this table, right? The only thing is that, well, actually the first one is at the bottom, and the last one is here. So if we flip this thing upside down, we would get that missing part of our generator matrix. So in my case, then the generator matrix is going to be like this: 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. That is identity matrix, right? And now I need to put this as well. So basically this is the first, that would be 1 0 1. This is the second, 1 1 1. The third is here, 1 1 0, and the fourth is here, 1 1, like this. This is our generator matrix for cyclic code, which, well, really isn't difficult to create if you have already calculated this table of the syndromes, right? So let us input that into our program now. For encoding Hamming, that is the only thing we are going to need to change here are these three last columns. That would be 1 0 1. This one would be 1 1 1, 1 1 0, and 0 1 1. That is for encoding matrix. Now for decoding matrix, we need this matrix of syndromes yet again in reverse order. So basically, yes. So basically, we need to actually put that in upside down order as the matrix of the syndromes in our decoding Hamming here. So the first one would be 1 0 1. The second one 1 1 1. Third one 1 1 0. 0 1 1. 1 0 0. And the rest is quite easy. That is actually the I matrix. So meaning actually meaning that we have, you can see here, the very same part. For encoding matrix, we put I matrix here with the 4 elements. For decoding matrix, we put I matrix here with 3 elements, right? So basically, this is the same part. Well, as it should be. As you know, you are encoding by calculating division with a certain generator polynomial and decoding with a certain generator polynomial. Even more so, if you look closely, that generator polynomial can be seen here. 1 0 1 1. That is with what we have divided, right? This is actually a shifted version of that polynomial, right? It has some shift, and well, that's how it's actually made. But that's not all what we need to change. Now we need to comment that part because this is not group code, so we need to keep that commented. Next thing is, at the end, we need to have this line uncommented because we have systematic code, meaning that first k columns actually contain our information. And then we need to correctly input the error position vectors, right? So this is the most tricky part of the cyclic codes. So because how our decoder here is organized is it converts the syndrome into the decimal number and then in according position performs correction. However, in this case, it's not true. Yes, you can see that, for example, syndrome number after conversion that would give 1. However, the error is in the position 7. Here we have 7 and the error is in position 2. So they completely do not match. So we need some conversion table which we apply to these syndromes so that this becomes correct, right? And our task is to create that conversion table. That conversion table correction index is here, right? And we need to fill it in. So how do we do that? So the first position is always 0. So that matches the case when there are no errors. And we still have to work out that case. And error vector in that case is all zeros, right? So let me again show you this. Error vec table, right? So this is the first case. Now, remembering that MATLAB actually has to add +1, which is considered here, right? So here we add +1. That becomes as 1, and we read the first row of this matrix, which happens to be all zeros, meaning that we don't make any error corrections and everything is fine. So next, we need to correct this symbol only in one case when the syndrome is 101. That is 5 in binary system or on decimal system. So we are going to need and put that in the position number 5, right? So in the position number 5, we need to put 1. So that should be in the 5th place. But other than that, let us maybe show, fill in this vector consequently, right? So what do we need to put into 0 position? That was 0. Next is in the position 1, matching the syndrome 001, right? So this is actually the decimal form of the syndrome. We need to type in the error number symbol where has happened error. So we find that syndrome here, it is here. The error must happen in this symbol, which is symbol number 7. So we put in there number 7, the erroneous symbol number, right, for this syndrome accordingly. So the number of the column in this matrix is the syndrome, and the value itself is the number of erroneous position. So similarly, we work for the next syndrome, which is 010, and it represents the error in the position number 6. The next syndrome is 011, which is 3, right? So this is 1, 2, 3, 4, 5, 6, and 7, right? So we need consequently to read first this, then this, then this, and then this, and this. So now we work with third. That represents the error in the position number 4, right? So we type in 4. The next syndrome is 4, which matches the error in the position number 5. Here. Next syndrome is 5, which matches error in the position number 1. And that's when we got to this fifth column, right? So this is 0, 1, 2, 3, 4, 5. So if we have syndrome number 5, it will access this table, read the value 1, and will know that it should take the first row of this matrix. And that's how the error will be corrected. As I said, it's quite tricky, and there was an option to do the same for a group systematic code without this part, right? However, it's easy to make an error there, and well, in that case, the results will be worse than expected. And well, if we could avoid it, we did. But now we have to do that correctly. Now we did 5. Next is 6, which represents error in the symbol number 3. And the last one is 7, which represents error in number position 2. So that is that correction vector. If you have m equal to 31, well, then I'm sorry for you, but you will need to pay a lot of attention in order to correctly fill in entire 32 positions correctly, right? That is very important. Otherwise, you will not get smooth plots. So I will first show you if we did everything correctly, right? Well, hopefully correctly. So yes, we can see that error probability is decreasing, meaning that errors are corrected, right? And then it will show us on plot. Then I'm going to show you what happens if we make that incorrectly. And from that, you will be able to understand whether you were on the right path or you need to, well, maybe check again and calculate, right? So here you can see that actually we still have that decoding gain. Now, if I, let me for speed, reduce this number to 4, right? So that we can finish faster. Now I'm just going to put here, instead of correct order, just some, let's say, natural order, 0, 1, 2, 3, 4, 5, 6, 7, as it would have been for non-systematic group code, right? So for non-systematic group code, that table looks like this. So what will happen in that case? In that case, as you can see, actually, we have worse results than without coding, which is naturally because our error correction attempts were incorrect. We tried to correct errors in incorrect places, and that leads to incorrect corrections, yes, and worse results. So you need to make sure that you actually did fill in that line correctly, right? So if you have any difficulties or need me to check that, you are welcome to send me a message, but you will also need to supply me with this table of syndromes, right? So that I am able to actually help you. So likewise, if you have any questions about this coding, you can send me. Now I am finished with my own reports, so I'm again available at any time for you, and I will be happy to help you. So this concludes our course. This is the final task of your course project. I will add some information about it into these guidelines at the end, yes, so that you have additional material to check too. And well, you can use these function templates to improve your program, right? So that's it. Thank you for attention, and that concludes our course.